Hi guys, this is a continuation of the previous video on the linear quadratic regulator, also known as LQR. And to start, let's just review the previous video that we did. So we broke down the LQR problem. The linear system we have is xk equals xk plus 1 equals axk plus buk, and very general, b, the state is in Rn, and the control is on Rm. So as general as we can be, and we have a cost function J0. It's a quadratic cost function as we discussed, and the regulator problem says that given some initial state x0, we want to steer the system to either a fixed state, some Rn that is given to us, or some free final state, in which case we want to regulate the system to x equals 0. Okay, and we started to derive, well, we actually did derive the necessary conditions for an optimal control here. Let me just show you them here. We had three different conditions. Remember, we constructed the Hamiltonian, which is just the Lagrangian plus the Lagrange multipliers times the function f times the dynamics. And we had three different necessary conditions. We had the state equation, which is just the trivial dynamics, the linear dynamics. We had the co-state equation, and we had the stationarity condition. And from the stationary condition, we already got the form of the optimal control over here. But the problem is that we don't know what the co-states are just yet. So a little bit more work has to be done there. As far as the state and co-states, we saw that if you look on the right over here, we saw that they were actually coupled together, but in a very, very special way. Remember, this the dynamics of the state and co-states can be written in vector and matrix form as a Hamiltonian matrix. And a Hamiltonian matrix is a special type of matrix, if you remember, that satisfies this equality here. And we said that one interesting to point out is that the dynamics for the state, they go forward in time, because we have k plus 1 on the left and k on the right. But the dynamics for the co-state sequence, they actually go backward in time. And that is one of the defining characteristics of this LQR problem, for now at least. And we said that this problem for the state and co-state, it's a two-point boundary value problem. What does that mean? Well, we have two different points, we have two equations, and we need two boundary conditions, right? And one of the boundary conditions we already know is that x0 is given. The second boundary condition, though, comes from the type of problem that we want to solve. And remember, we said we have two different types of problems. We have fixed final state problems in which xn is equal to Rn, it's given, so that's two conditions right there. Or we have free final state problems. And in that case, if you look at the cost over here, whoopsie doopsie, if you look at the cost, this cost right here, for free final state problems, we actually have to add in this terminal cost, which I label as phi. And this terminal cost is needed in here because since we're minimizing this cost, we're going to minimize this quadratic form, which means we're minimizing xn. Okay, so that's where this is coming from, this phi function over here. And for a free final state, we actually have another condition, and again, this comes from constraint optimization, and it says that the lambda n, the co-state at time step n, is equal to the derivative of phi with respect to the state. And all this gives us is just the derivative of quadratic is just a linear. And since we assume that Sn is at least positive semi-definite, we get this expression over here. So in any case, no matter if we're dealing with fixed state or free final state, we have two boundary conditions to solve this problem. But since they are coupled like this, there is no analytical solution yet. Okay, but that was enough review. I think we get the picture now. Let me hop on over to the topic of today's video, which is a bit of an interlude, but it's an important interlude because it's going to set up a lot of things for videos to come. And in today's video, I want to look at the zero input cost and what it reduces down to. And we're going to see it reduces to a very special type of system, well, equation, that's governed by the Lyapunov equation. Okay, so let me change slides real quick. Alright, so I cleared the page and we are ready to go. So what do I mean by zero input cost? Well, all this means is, remember the cost from before is just J0 equals 1/2 x transpose SMX plus 1/2 sum from k equals 0 to n-1. And then we have the state, inner product, quadratic form, plus the control quadratic form. And this is our cost. And note that I put a little subscript 0 here. And I didn't do this because I'm a fancy guy. I did this because it's very important. Because in this zero input cost, we want to calculate what is known as the cost to go. So let me write that here. Cost to go. And this is a pretty important concept that I want to introduce. So let's say, let me draw some axes here. And let's say we want to compute the optimal control from point A to point B, right? That's our LQR problem. That's what we started with originally. J0 would be the cost from time k equals 0 all the way to time k equals n, right? So if I have a graph of k on the right hand side and ji on the left hand side, then at k equals 0 we're going to have some value, right? And as we go along k all the way to all the way to n, these values are going to get smaller and smaller and smaller, because the cost to go, since if we're already here, the cost to go is smaller than as if we are just originally starting, right? It's a very intuitive concept. And there's a whole formulation of optimal control based on this guy named Pontryagin. And he basically said that the optimal control, if we're at time step I to n, is independent of the optimal control here. Meaning that the cost to go should be the same as if all the controls were applied and we're here now as their initial condition. And something like that. I don't remember the exact details, but it goes along that partition method. And that's how you get the Pontryagin minimum principle of optimal control. So there's just a little historical context here as to why we're calculating this cost to go quantity. But it is also important later on. Anyways, enough of me rambling. Let's get to some calculations. So, zero input cost. Obviously, in a zero input cost, our input or control is 0. So this guy goes away. And we're just left with this equation right here. And also, I'm going to change the zeros to i's. And the reason why I just said is because I want to calculate the cost to go, which is ji. Okay? And this can be applicable for all time steps. Now, what do I want to do next? I want to see what is, let me pick a different color here, what is Jn? Well, clearly, Jn, this sum goes away and we're just left with the terminal cost, which is 1/2 xn transpose Sn xn. Okay, that's easy enough. But now I want to calculate a different quantity, which is J, the cost to go, not the terminal cost to go, but the cost to go at time step n-1. And we see that's going to be almost the same thing. We're going to have the same first term, right? If we just look at this. But now we're going to have one term from this running cost. And since the control is 0, this is a 0 input control. We're just going to have 1/2 xn-1 transpose qn-1 xn-1. But now I'm going to do some little tricky mathematics. And what I'm going to do is, I'm going to plug in the dynamics at xn. And recall the dynamics at xn is just n-1, xn-1, plus bn-1, un-1. No control, so it's just the simple update equation. Okay? And I'm going to plug this in over here. And let's see what happens. Okay, let us see what happens here. Let me get a different color. Okay, so when I take the transpose, I will get at the end xn minus 1 transpose, because I'm replacing xn. And then in the parentheses over here, I'm going to have n minus 1 transpose Sn, an minus 1. And then also I'm going to have the q over here, plus qn minus 1. And this whole thing is inside this quadratic form. So look what's happening here. It's very interesting. Let me define the quantity Sn minus 1. And this quantity is defined as an minus 1 transpose Sn, an minus 1, the whole term in the parentheses basically, right? And look what ends up happening. This implies that Jn minus 1 is nothing more than 1/2 times the state at n minus 1 transpose times this matrix S at n minus 1 times xn minus 1. And this is really important. Look at this and then compare it with this guy right here. And we notice it's the same exact thing. So in fact, we can generalize this. And we can say that without loss of generality, that J of I is equal to 1/2 xi transpose Si and then xi. I equals 0 to n. Where such that Si is equal to, now we just generalize this guy right here. So Si is equal to Ai transpose times Si plus 1 Ai plus Qi. Okay, and this equation is very important right here. This equation is the update equation for this S matrix that I've defined. And since this is a, well, in continuous time it would be a differential equation, but in discrete time it's a difference equation. So we always need a boundary condition, right? And in this case it is Sn, because we are given Sn. Sn is given. This is our terminal weighting matrix from all the way before. But I just generalized it to a sequence. And this matrix S is actually called the kernel. It is called the kernel. Okay? And this equation that I've written down here, it's a very famous equation. It's called the Lyapunov equation, after the Russian mathematician. Lyapunov equation. Okay? And if you've ever studied control theory, even in the slightest, the Lyapunov equation is extremely important in stability analysis. Okay? And it looks very similar to this. In this case, it's called the discrete Lyapunov equation. But there's also the continuous time analog of it as well. Okay? But this is the form of the cost to go. We see that it is in fact a quadratic form itself at every time step, where this kernel over here satisfies a Lyapunov equation, difference equation. Okay? And why I wanted to talk about this might not seem like very much right now, but later on when we solve the full LQR problem with non-zero input cost, with non-zero inputs, we're going to see that the optimal cost to go, okay, is going to be J star in that case, is going to be the same exact formula. Okay? The only difference, though, is that this Si, this kernel matrix sequence, is not going to satisfy a simple Lyapunov equation anymore. It's going to satisfy what is called the Riccati equation, which is a bit more complicated but also more rich in structure. So this is all I wanted to talk about in this video. Give a gentle introduction to the Lyapunov equation and see how it shows up in the LQR problem. So next video we're gonna actually solve this LQR problem, and we're gonna talk about some of the results, and we're gonna derive the famous Riccati equation. So that's exciting. See you then.